Let's commence recording. Anyhow, I forgot to record. What we're going to do is we're going to talk about some examples that illustrate the things we talked about last class. So the first example is we have a local business. It wants to assign 7-digit numbers to their employees. I would encourage you to think about this. Every one of you has a number. You have a student ID number. I don't know how many digits it is. What is it? I should have looked it up. Who cares? The point is sometimes we might want to assign numbers to employees. Why? Because maybe if I'm in payroll, I don't need to know what everybody makes. Do I need to know that John Smith makes this? Do I need to know what your situation is? No. So you have a number that keeps security, whatever. Right? Makes sense. So here's the question. How many possible employee numbers are there? So how many different employee numbers can we have? So here's what we're going to do. We will assume digits can be repeated. So for example, my number could be 1, 2, 3, 4, 5, 6, 7, right? Or my number can be 1, 1, 1, 1, 1, 1, 1, right? 7 times. Does that make sense? So do we understand the problem? If you don't, please ask. So each one of us gets, and let's just sort of write this out. So, so person 1 could be 1, 1, 1, 1, 1, 1, 1. And then person 2 could be, say, 1, 2, 1, 1, 1, 1, 1, etc. Does that make sense? So the question is, how many possible do we have? So the quick way is to just resort to the fundamental property of multiplication, but let's sort of spell it out, so to speak. So digit 1 has, how many digits are there? How many digits do we use in the conventional number? What do we have? We have 10 digits, right? 0 through 9. Digit 2 has 10 options, 0 through 9, etc. So this goes all the way down to 10, and we had this fundamental counting principle that says the following. Thus, there are 10 times 10 times 10 all the way up. How many times? 7 times, which is, say that again?
10 million? Or 10 to 7?
10 to the 7th, yeah. But you going both languages here?
Yeah.
Is that what you said? Did you say 10 nueve? Or am I not hearing you? Is that what you said?
I said 10 to the 7.
I know, but I swear you said it in Spanish first. Did you? I don't care. I hope you did. Or what did you say?
10 million.
10 million. I thought you were trying to be nueve. Ain't that 7 in Spanish? Of course, you don't even do. Why do I assume? No. Uno, dos, tres, cuatro, cinco, seis is 7. Siete is 7. Ocho is 8. Nueve is 9. Si, oui. No, that's French. Boy, damn. Right, and what's 10 to the 7th? what is 10 to the 7th? Well, you can either multiply out or you could count zeros. I don't know how you guys learn to do your powers. But that just means that there's 7 zeros here. So that's 1, 2, 3, 4, 5, 6, 7. So if you want to spell it out, that's 10 million. What you said, right? So let's say possibilities. Tell you what, my spelling has become suspect in my old age. You know what? That does have something to do with it, I think. But also, I think it's worse here than it is writing on the board. But writing on the board is worse than when I'm typing. For example, I think it's just some weird connection with your mind. It's hard sometimes when you're standing on a board and you're writing, or I'm trying to multitask up here. I don't know what happens. But I notice I make far more typos when I'm teaching than I do if I'm just typing something up. Does anybody have a question about this problem? So on homework, I asked you to do this for 5-digit zip codes and 9-digit social security numbers. So I hope you get the analogy here. For zip codes, it's 10 to the 5th, right? For social security numbers, it's 10 to the 9th if there's 9 digits. All right, then the next problem I asked you to study is something like this. So I don't want to do the same example, but I want to give you some insight on how this works. So this is example 2.
I have a question about
Yeah,
this
what's your question? Yeah.
So like, say if you want to repeat the number.
Yeah.
Then how would you do that?
Okay, then that would be the factorial. How many options would you have for the first digit? You'd have 10. So how many options do you have for the next digit? 9, then 8, all the way down. That's right. So the question was, what if we weren't allowed to repeat digits in each number? Then you would use 10 factorial, 10 times 9 times 8 times 7 times 6. So which is bigger, 7 factorial or 7 to the 7th? Now, the efficient way to answer this particular problem would be to go to a calculator. But that doesn't give you any insight to what's happening. Because guess what? When numbers get big, calculators don't help you anymore. They just don't. Because calculators start rounding. So let me remind you of this. I'm going to go to the internet machine. And I'm going to go to the calculator. So Google can do these things. What if I said 7 factorial? 7 factorial, according to Google, is 5,040. That is an accurate number. It's not lying to me. And then if I also wanted to do 7 to the 7th, I would say, okay, 7 to the 7 is, 823,543. So clearly using a calculator, we know that 7 to the 7th is bigger. Now, that's fine. You can answer the question that way, but then you miss out on learning things. You miss out on patterns. You miss out on something that can help you later. So for example, what if instead of 7, what if I asked you what's bigger? 70, say, how about 100 factorial? Google gave up. Do you think that this is 100 factorial? You might think it is, but that would be very random, because what is this number? You do whatever you feel best, Soren. You're cool, bit. You don't have to worry either way. What this number says, for those of you who forget what we mean by scientific notation, is this is 9332622 with 157 zeros. Do you think that this number has 157 zeros at the end of it? That would seem highly unlikely. So what Google's doing here is Google doesn't have enough memory allocated to give us the exact number. So it rounds. Now, guess what? There's better calculators out there. There's this place called Wolfram Alpha, who I think I've showed you before. It is a wizard. It will tell us most likely that 100 factorial, it will give us to us exactly. There it is. There it is exactly. So it doesn't have 147 zeros at the end or whatever. It just has a few zeros at the end, relatively speaking, right? So the point is, with large numbers, calculators run out of memory. In fact, computers in general can only have a largest number. They can only have a smallest number. Computers only have so much memory to store things. And you people like video game people and understand things like when we were kids, it'd be like 8-bit, 62-bit or 64-bit and all that. All that matters is how much, what that means is how much information we can store. So if you've ever had to update things for your computer, sometimes if you have Windows, it'll ask you, do you want like 32-bit or 64? And what that has to do with is how much memory it allocates to certain things. So when we're putting numbers in a computer, there's only so much memory to store numbers. So we have a largest and a smallest, and the rest we round. So the fact of the matter is, if we go back to our problem here, the most efficient way to answer this question in general is to not go to a calculator, because a calculator might lie to us with big numbers. It doesn't mean to lie to us, but it might. So a more efficient way to answer it is seven factorial by definition is 7 times 6 times 5 times 4 times 3 times 2 times 1. And 7 to the 7th is 7 times 7 times 7 times 7 times 7 times 7 times 7. So it's clear then, and let me tell you why it's clear. Since 6 is less than 7, 5 is less than 7, 1 is less than 7. It's clear that 7 factorial must be less than 7 to the power 7. So the way I'd like you to think about this is think of it vertically. These numbers are the same. The first number in each one is the same. Then here, 6 is less than 7. 5 is less than 7. 4 is less than 7. So if I multiply these all together, it can't be bigger than multiplying all these together. That's the way I'd like you to think about it. So here's an even bigger fact in general that might be of use. Fact. See, by looking at the problem that way, we see a more useful idea. If n equals 1, 2, 3, 4, 5, if it equals any number that is a counting number, then n factorial is always less than or equal to n to the power n. Does anybody have a question about this? This fact actually has lots of consequences too in many different areas. So it's also, again, we're trying to give you some basic ideas and patterns in counting, and they're going to be useful for us in what we do coming up soon enough. All right, so does anybody have any question about this? All right, let's look at one more example before we move on. So let's list all the different ways that we can arrange the letters A, E, and I. So we did this problem in a different way on Monday. So we have 3 factorial, which is equal to 3 times 2 times 1, which is 6 ways. Why? Because the first spot has 3 choices or options. Second spot has 2. And last spot has 1 choice or 1 option remaining. So if you wanted to list these, you could. There's 6 of them. We did this with the letters. I think cat, I think we did it with the other day. It's worth doing it again. So what are they? Let's list them real quick. So the first way would be like A, E, and I. Then you could do A, I, E. Then you could do E, A, I. You can do E, I, A. And then the other 2 would be I, A, E, or I, E, A. 6 total options. Does anybody have a question about this? All right, so this is there's a name we give to this type of arrangement. So So we have 3 objects in a specific order. So we call this a permutation. So this is often confusing for students. What do we mean by in a specific order? Well, I'm thinking about it in the sense that we're not reusing. If I have the letters A, E, and I, specific order means that I can only use them each once. Now, how do we sort of understand the difference between that and maybe some other scenarios? So currently you might say, okay, well, what do you mean by specific order? Well, let's think about back to some of the problems we had on the midterm when we were talking about pulling cards. So if I say we get 2 queens and a heart, per se, well, when you do that analysis, it does matter what comes first, right? So there, order matters. If I would say the problem, I get a queen, then a jack, that could be different than me saying get a queen and a jack. I'm not saying it will be, but it could be. Do we understand there's a subtlety there? Sometimes order matters, sometimes it doesn't, and we want to distinguish these two things. And so the mathematical words for this are, when order matters, we use the word permutation. And when order doesn't matter, the English word we use is combination. And it's not going to be clear right now why we need this, but it'll be clear, hopefully. It will be clear soon enough. And before I write anything else down, let's think about a better way to think about it is instead of me having, say I have 3 letters or 3 objects, suppose I have 10 objects. Or, okay, let's go to the more specific, the specific example, which I've been doing. Say I have 52 objects, I have 52 cards in a deck. Suppose I want to select 5 of them. I think you understand, or let's just say 3. Oh, heck, not 3, 2. We want to select 2 cards from a deck. I hope you appreciate and understand that when we talked about this idea of like conditional probability before, with a deck of cards, what comes second is going to be dependent on what comes first. So for example, if I am talking about getting 2 queens, then order doesn't matter necessarily. But if I say a jack, then an ace, does order matter versus an ace, then a jack? Well, it could or it couldn't, depending on a particular scenario. Do we at least, okay, so maybe we don't understand it yet, but at least we could say, okay, I understand that sometimes order may matter and order may not, hopefully. So let's define this officially, this idea of a permutation. So a permutation is an arrangement of n objects in a specific order. So clearly, using this definition, n has to be what we call a positive integer or a counting number. It has to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so let's look at an example to help illustrate something. Suppose we want to choose two letters out of M, A, T, and H. What are the options? Well, let's just go straightforward. I can get M and then A. So let's choose that I pick M first. So I can get M and A. And then if I get M first, I can also then get T first. And I can get M first, and then I can get H first. Now what happens if we pull A first? If we pull A first, we can get AM, we can get AT, we can get AH. And then if I pull T first, I can get TM, I can get TA, or I can get TH. And then lastly, if I pull H first, I can get H, and then I can get M, I can get H, and then A, and then I can get H, and then T. So if we think about it, we've exhausted all things, and we notice there are 12 options. Does anybody have a question about this? Comment. Now, you could generalize this to the cards. Instead of having 4 letters, we could say, I'm going to have 52 cards. What are the options for picking 2 cards? Well, then it's a lot more options, right? You could start like ace, you know, right? It'd be a lot more difficult. But you could do it if you wanted. If you took the time, you can do it. Now, of course, we know that there's got to be a better way than listing all these out.
So if this is a combination then, and then
This is not a combination, not yet.
Oh, wait. So this is the permutation.
Right, no, okay, so no, but we didn't even talk about combination yet, but this is, hopefully this will help clarify it. So we're calling these permutations because this is an ordered list. Each one of these 12 has an order. Now, if we don't care about order, for example, if we don't care what order we chose them in, then something like AM would be the same as MA. Does that make sense? And MT would be the same as TM if order is irrelevant.
So there's only 3 combinations.
Well, no, it's going to be more than 3. You're close. Yeah. So what happens? Let's get to that. So let's first note, let's put this down in terms of formulas for a second. So this says that there are 12 permutations when selecting 2 objects from 4. That's what this says. So before we talk about combinations, we need to ask, is there a pattern? Is there an easier way for us to get this number than to actually list it out? Because what if I said to you, how many ways can I choose 2 from 52? Do you want to list all them out? At least in this smaller case, we can list it out. We can feel confident we've exhausted all possibilities. But if I said to you, write out all the different permutations when you select 2 objects from 52, that's going to be massive. Right? Because you think about it, that'd be a very massive list. And not only that, not only would it be massive, you would be so unconfident in your abilities to make sure you had them all. And so we figure there's got to be a rule to doing this. There's got to be sort of some pattern that we're missing. So what is the pattern then? So let's ask ourselves that. So is there a pattern to obtain this number without actually writing everything down? That's what we're hoping to understand. And it turns out if you analyze what we just did and you study it from sort of a different perspective, you'll see that. So one of the themes, and I don't know if you pick up on it, maybe you hate me, you hate this class, I don't know. But one of the things I've tried to at least convince you of is that when you're doing lots of things, particularly in a class like this, and really in many areas in math, going right to a calculator and doing arithmetic, you're missing out on patterns. And one of the beautiful things about modern mathematics, and not just the math that you know, maybe some of you know a little bit of calculus, or maybe some of you know other math, is one of the beautiful things about math is about recognizing patterns and looking for ways to take complicated ideas and complicated calculations and finding simple ways of doing it. That is one of the main sort of themes of advanced mathematics, understanding patterns in simple ways. Now, of course, you're going to say, I don't know what the hell you're talking about, because most of you have never done math outside of what we call school math, and that's algebra and a little bit of geometry, and maybe some of you were lucky enough to do calculus. Notice I said lucky, right? Yeah. And there's so much other mathematics out there that many of you will never get to learn because you're afraid of it. And that's all the cool stuff, because they didn't teach you in school. They taught you the boring crap like algebra. Blech. Anyhow, the fact of the matter is if we look at this, can we figure something out? So let's think about this in terms of our multiplication rules. How many options do we have for our first letter? There's 4 options, right? How many options do we have for our second letter? 3, right? So one way to think about this is to say, okay, if I have 4 options for my first and I have 3 for my second, oh, 4 times 3 is 12. That makes sense, right? We follow that? Does that mean in general then that if I want to choose 7 objects out of 52 or 3 out of 1,000, that it's always going to be 1,000 times 999? Do you see what I'm saying? Maybe you don't. I don't know. I always say, do you see what I'm saying? Or do you understand? And you're like, huh? I say, do you have any questions? And you're like, huh? Uh-huh. 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 Is there a formula for this? So let's come back here and let's ask, well, or so for the first letter, we have 4 choices. And for the second, we have 3. So in one hand, thus 4 times 3 equals 12 seems reasonable. And not a coincidence. Okay, so let's say we play the game differently. What if I wanted to go one step further? If I wanted to choose 3 out of the 4, I would still have 4 for the first choice. I'd have 3 for the second, and then 2 for the third, right? So in general, choosing K objects from N gives us the following: N times N minus 1 times N minus 2. Now, this is going to be very scary, but if you think about the pattern I just suggested, this goes all the way down to N minus K plus 1. Now, this looks very frightening, but how many of these terms are there going to be? There's actually K factors. So let me illustrate that again. If I want to select 2 out of the 4, I have 4 times 3, that's 2 factors. If I wanted to select 3 out of the 4, I would have 4 times 3 times 2, that's 2 factors. So the only thing that's going to be scary for us in a position like you're in right now is you see this scary thing, N minus K plus 1. But there's a simpler way of writing this. This can be written in a much cleaner form. So this scary formula that I have written at the bottom of the page is scary. It seems like, ugh. But there's actually one that is, well, to you is going to be scary, but it's much, much simpler to remember. So Turns out the K factors on the previous page are equal to this, n factorial divided by the quantity n minus k factorial. And so this number is so important, it gets a name. We denote it with a capital P, and then we put N and K like this. And we write it. And I know it's scary, but it turns out to be very, very useful. So look, on the next page, we're going to do some specific examples, and I hope it sort of takes your, for those of you, I know some of you are like, your head's going to explode because there's symbols that you don't like. But it is what it is. I wish there was an easier way. I wish I can give you guys a magic pill and everybody would be waking up tomorrow and say, oh my God, this is easy. But that's not how it works. There are very, very few human beings on this planet that can learn this stuff in 5 minutes. Most people require a lot of effort to learn this stuff. All right, does anybody have a question about this before we do some examples briefly? All right. So let's just go right to the problem we did. If we do in these scary symbols, the problem we had, the number of permutations of 4, 2, by definition, this is 4 factorial over 4 minus 2 factorial. And that's 4 factorial over 2 factorial. And you can write this out. It doesn't matter how you want to sort of do this, but if you want to make a connection with our example, you can do it this way, and you'll notice that these common factors go away, and this is 12, as we had before. Okay, does anybody have a question about this? Yeah, it is, but you have to understand. Yeah, okay. Because this in the problem we did, I'm using 2. This is selecting 2 objects out of 4. So let's just do one more, and then I will remind you what this says. If I say 52 of 2, so this would be the number of ways that I can select 2 cards out of 52, for example. This would be 52 factorial over 50 factorial. And this simplifies, I'm not going to write it all out, but this is just going to simplify to 52 times 51. Now, if you could, you can do this 50 times 49 all the way down to 2 times 1 over 50 times 49 all the way down to 2 times 1. But all these things cancel. And you're left with 52 times 51. Which is what, 26, 51? 2652. By the way, people always say, how'd you do that in your head? Can anybody do 52 times 51 in their head real easy? Not that you have to be able to, but there's a shortcut for doing it. Algebra class gave you that shortcut. Just a reminder that if you wanted to, for fun, 52 times 51 is the same as 50 plus 2 times 50 plus 1. And then this is, what's 50 times 50? Well, that's 2,500 plus, what is 50 times 1? Well, this would be, the middle terms would be 150. And then the last term would be 2. So that's how you do it in your head. Not saying you have to do it in your head, but you ever meet people that can do this crap? That's because they ain't like weirdos. They just train their brain to store information like a piss poor computer. Seriously, I remember growing up with kids that can do this. I was like, what is wrong with you nerds? And I realized, why not? It's fun. It's good mental exercise. Just like I get down and give you 25 push-ups, right? Why not? We exercise our muscles. Why not exercise our brains? I'm not saying you should do that, but that's one way to do it in your head. Of course, we better check it in the calculator. Yes, okay. That would have been bad if I got that wrong. Would it not have? Remember the old FOIL method? All that crap they taught you in algebra? See, that's another thing. Have you ever thought about how do calculators do arithmetic? Have you ever pondered that? I have a rule. If I ever become president, which who knows, but if I ever become president, I will mandate that no one is allowed to use a calculator unless they know how the damn thing works, right? That'll be my rule. Like, you know, old people say you shouldn't drive unless you know how to change the oil or something. Well, that's stupid, but you shouldn't use a calculator unless you know how it works. Right? Can't use a microwave unless you know how it works. No electricity unless you know how it works, right? What do the vegan people say? Would you eat animals if you had to kill them? And yes, I probably would.
Yes.
I like steak. Yes, I do. Yes, I do. Even though I don't hunt. Okay, so that was fun. I love this class. You guys are so cute. So again, what does, if I write P n sub k, this is equal to the number of permutations of k objects out of n, and since it's permutations, that means order matters. All right. Now, let's go back to what the example that we had, and we got to think about what happens if we do care about order. What if order does matter? Okay, so let's go back to our example of selecting two letters from M, A, T, and H. So I'm going to go to the next page, and let me just, I'll slow down in case you have questions, preguntas. So let's recall what they are. We had MA, we had MT, we had MH, and then we had AM. We had what was after BT, and then AH, and then we had TM, and then we had TA, and then we had TH, and then lastly HA. Oh, excuse me, HM. You got a clothing store for the kids, H&M. HM, HA, and then HT. So if order doesn't matter, then MA is the same thing as AM. And we can remove them, the duplicates. So for example, that's a duplicate. And if we go down the list, we have, so MA, we got rid of its duplicate. MT and TM are the same. MH and HM are the same. Then AT and T, well, excuse me, I don't want to delete them all. TA is the same as AT, and then HA is the same as AH. And then, of course, HT is the same as TH, so we get rid of this. So effectively, what have we done? We've cut our list in what? We've cut it in half, right? So now we have six options. So what do we need to do then? It's only coincidence this time that we cut it in half. What we really did is we removed all the duplicates. So how many, what were we choosing? We were choosing 2. So that means since we're choosing 2, we're going to have 2 factorial duplicates. Now that might not be as obvious to you. That's even if the other stuff was clear. So here's a useful fact. In general, if we are selecting K objects from N, there are K factorial duplicates. Well, okay, I wrote that wrong. That doesn't make sense. Stop for a second. Stop for a second. That was bad. I said that incorrectly. Because really, there weren't K factorial duplicates here. There weren't 2. How many duplicates did we have? We had 6, right? So what's a better way of saying that? Does anybody have any ideas?
K objects out of a number of N. And then I'll put from there.
Well, right, but how? Okay, let's just put it, it's not going to be half, but okay, let's just write it down first, and then you can maybe think about it. So in general, if we're selecting K objects from N and order doesn't matter, we have the following. So it's N factorial divided by N minus K factorial times K factorial. So we have this many options. So we call these combinations and denote by C sub NK, or we use this. Looks like a fraction, but it's not. It's N over K in these parentheses. I guess I should spell this correctly. So let's think of a real world scenario where there's a difference between permutation and combination. Suppose I go home and I say, okay, I'm going to take my bookshelf, which probably has a couple hundred books, and I'm going to pick 5 of them and I'm going to send them to my brother so that he can read them. Now that would be different than me saying I'm going to pick 5 of them and assign them for homework in a class where book 1 will be the first assignment, book 2 would be the second assignment, etc. In one scenario, the orders matters. In the other scenario, it's irrelevant. Do we understand that? In a poker hand, it doesn't matter if I make a hand. It doesn't matter what order I make a hand, does it? In traditional poker, but if I'm playing a game with cards where it does matter if I get something first as opposed to second, then it does matter. Like, let's say I'm playing a card game where I'm just playing you and me heads up, like war. Suppose in succession, I get a king and a 5. Well, if I get a 5 first, I might lose to you, and that king, which would have came, never even matters. Does that make sense? So there are times when order is important and there's times when order isn't. And that's why we have these different options. Now, what would be a good learning exercise for you is to understand why the only difference is this factor of K factorial down here. Why is that down there? So if that's the only difference, it means dividing by K factorial somehow removing the duplications. But why? Why is it removing the duplicates? Well, we're able to reason the formula for permutations, but this one doesn't seem as obvious why it is what it is. Well, let's go back to the picture and think about it. Okay, when I go with my first option, which is MA, since I'm only choosing 2, how many possible duplicates can there be? There can be 2 duplicates, right? And then when I go to my next option, MT, since there's only 2 letters, there can only be, okay, let me rephrase, slow down. I misspoke. There can only be 1 duplicate. But then I can have 1 duplicate for MT. I can have 1 duplicate for MH. I can have 1 duplicate for AT, 1 duplicate for AH, and then 1 duplicate for TH. So for M's, how many duplicates can I have where I start with M? I can have 3. Right? And then for how many duplicates can I have where I start with A? 2. And then how many duplicates can I have where I start with T? Just 1. And so that's one way to think about how this factorial pops up in the denominator. I would encourage you to think about it. I'm not saying it's easy, but remember, we're saying this is a definition. So this is, I shouldn't say it's, maybe definition's a bad word. It's really like a counting rule. Does anybody have a comment or a question? So we're going to give you some problems to think about this, and that's the best way to learn it. All right. So things you should be able to do. You should be able to compute P sub n, permutations nk, and combinations nk, both by hand and using calculator or software. It's not hard to do it. Google will do it for you. That website, Wolfram, you could probably just Google permutation calculator, combination calculator. It's easy. So, and by the way, if you for the combinations, so it might be useful to read the combinations, this guy as n choose k. So for example, if I go to the Google machine, so say I just go to Google and I type 4 choose 2, it's going to spit out 6, as we saw, because that was half. Does that make sense? Or half of the 12. So, and if I do, say, 52 choose 2, I get 1,326. How about, here's a cool one. What is 52 choose 5? So how many possible poker hands are there? It's a big number. 2,598,960 possible poker hands. Again, why am I using choose for poker hands? Well, it doesn't matter. If I get, if I get a straight, it doesn't matter what order I get the straight in. Does that make sense? But what happens is when the numbers become big, some calculators aren't able to do this. So you have to learn how to do it using any handheld calculator can do it. If you just Google things like permutation, calculator. There you go. There's the formula from Google. Here's a calculator. You can plug it in. What did we do before? We had 4, choose 2. And if we calculate, we'll get 12. Bingo. Oh, it even shows you. How cute is that? Easy. All right, any questions, comments? All right, thank you guys very much. I will see you next week. Please finish this homework that I signed the other day, and then I will see you guys Monday. Thank you very much. Take care.